Hello, y'all. Welcome to Lesson 10, Structure 1.3.5. We're going to be talking about electron configurations. So what will be covered is that each orbital has a defined energy state for a given electron configuration and chemical environment and can hold two electrons of opposite spin. Furthermore, sublevels contain a fixed number of orbitals, regions of space where there is a high probability of finding electrons. We covered that a little bit last lesson. We will be able to apply the Aufbau principle, Hund's rule, and Pauli exclusion principle to deduce electron configurations for atoms and ions up to Z36. What we're saying here is atomic number 36, so 36 protons, 36 electrons. Couple things is full electron configurations and condensed electron configurations using noble gas should be covered. We'll cover that. We should be able to draw orbital diagrams. Arrow in box diagrams is another name for them. And we should be able to represent the filling of relative energy of orbitals. And lastly, we're going to cover the exceptions, chromium and copper, of the Aufbau principle. So, with that said, this is going to be a little bit of a longer lesson, but let's jump in. So, what is the electron configuration? Well, the simplest way of talking about it is that just shows the arrangement of electrons within their orbitals. So we're going to be able to show where each electron is within its orbital. And furthermore, this helps us because we have to fill orbitals with electrons following three principles, which I mentioned in the top of this. So we're going to cover these three principles first. So number one is the Aufbau principle. So the Aufbau principle is our most important, and we kind of use these almost in order of how we apply them, and we'll cover that too. But the Aufbau principle just says that we fill lowest energy orbitals first. That's kind of like when we're talking about n equals 1, n equals 2, dot, dot, dot. As we move forward, we want to start with the low energy. In our energy level diagrams before, n equals 1 was the bottom, that was our ground state. And so Aufbau says we fill with the lowest first. It's kind of like if you're going to build a house, you build the first floor, and then you build the second on top of it and third on top of that. I honestly don't know. I don't build homes, but maybe if you're doing it with Lego or something, you can't put something above nothing, otherwise it will just fall. So that we want to take that into account as we add electrons to an atom. Number two, we have the Pauli exclusion principle. Now, I'm going to say that you don't necessarily need to memorize these names. You just have to understand how to use these rules, and you're going to get a lot more practice using them than learning the names. But this tells us that each orbital can only hold two electrons. We already knew that from our previous lesson, but we're going to add something with opposite spins. So we don't really need to understand spins too much, but generally we say there are electrons are either up or down. They are quantum particles and they spin, almost like the Earth spins around its axis. Electrons also spin. And so when we put two electrons together, so when these two come together, they need to have opposite spins. We cannot put them together with the same spin. So that's all we have to know about it. They have opposite spins. Moving on. Number three. This is Hund's rule. Hund's rule. Hund's rule basically says that when we fill degenerate orbitals, and degenerate orbitals are just orbitals of the same energy. So when we're filling two orbitals of the same energy, or 3 or 5 or 7, uh, we, I should put a comma there, each orbital gets one electron before doubling up. So we put one electron in each orbital before we double up. So if you were maybe imagining our p orbitals from the last lesson, I said there are three p orbitals every time. We have px, py, and pz. If we have three electrons, we would put one electron here, one electron here, one electron here. If we have four electrons, then we could double up. We could put a new electron there. But each one would get one. We would not have, in the same case, one electron, two electron, three electron. This is breaking Hund's rule, so we don't have that. We like to do one first. All right. So with all that, I'm just going to kind of delete this because we don't actually need it. And we will get on trying these things out. So as we move forward, the first thing we need to do is figure out what energy each orbital has. So we're going to use what we call energy level diagrams. Energy level diagrams. We already did energy diagrams with each main energy level, 1, 2, 3, 4, 5, 6, so on. And we noticed that 1 was always lowest, but we can use energy level diagrams to assist us in showing which orbitals have the lowest energy, especially when we have different sublevels too. So this will help us with S, P, D, and F. So a good example might be N equals 4, the fourth energy level, fourth main energy level. So we have our energy on our y-axis again, and we have our orbitals. So this is our 4s sublevel, our 4p sublevel with three orbitals, our 4d sublevel with five orbitals, and our 4f sublevel with two, three, four, five, six, seven orbitals. So we can see that if we were to put electrons in here, we would put them in the 4s, then the 4p, then the 4d, then the 4f as our energy increases going up. So according to our rules, we would fill this, then this, then this, then this. All right, so this is what an energy level diagram looks like. But what if we have more than just n equals 4? Well, give me just a moment and I will pause it and come back when I pull that diagram up. All right, we're back and we have this energy level diagram all the way going from 1s to 6s. And we'll notice a couple things. Just like our energy levels, the gaps between 1s and 2s is largest, then 3s, and eventually the gap between 5s and 6s is the smallest. So the difference in energy is still converging as we move to those higher energies. Another thing to notice is that 1s is lowest, 2s and 2p are the next lowest, 3s and 3p are the next lowest, but then 4s is actually lower than the 3d. So as we fill these orbitals, we're going to fill 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. So we're going to fill orbitals going from lowest first, and 4s will have lower energy than 3d. So let's just clarify those points. So first off, I want to clarify about degenerate orbitals again. Degenerate orbitals will all have equal energy. And we can see that. So our degenerate orbitals might be like all of the 2p's, which will have equal energy, or all of the 3d's. These are what we would consider degenerate orbitals. This 3D, this 3D, this 3D, this 3D, and this 3D all have the same energy. Point two is that there is overlap between D and S orbitals, and that's specifically where you see it at 4s and 3D and 5s and 4D. So we have to make sure that the lower energy one is filled first according to the Aufbau principle. All right. So how do we fill these in? Well, I actually have a trick for filling in orbitals. There's a bunch of different tricks out there. Some of them have you do 1s, 2s, 2p, and you kind of go like in a zigzag, or I honestly don't use that method. So you'll see it on books and you'll see it on Cogni, but I use a method that's, in my opinion, far more reliable because you will always have a periodic table with you. You may not always have that little chart that tells you. So if we look at our periodic table, we actually generally split it into blocks. We call this the S block, the D block, the F block, oh, oops, sorry, the P block, and the F block. And here's our lanthanides and actinides, but you won't have to worry about them for the DP curriculum. Furthermore, helium actually doesn't belong here on the P block. Helium gets moved in its rightful place in the S block. So this will be helium. Then we must account for our periodic table. 1, 2, 3, 4, 5, 6, 7. So we're going to account for our energy levels. All right. So when we go through and assign energy levels to atoms, which will be far more clear once we do examples, you do it like you're going to read a book. When you read a book, you generally start in the top left and you read, then drop a line, read, then drop a line, read, then drop a line. So we're going to do the same thing. So I look here and I go 1s block. So I will start with 1s. As I look across, there's nothing because we've removed helium. So I drop 2s. So I will then write 2s. I will continue to read across. And that's still energy level 2, but now P. Then I drop down and I see 3s. Then I read across and I go 3p. Then I drop and we hit 4s. Then 3d. We know it's 3d because we know that we have our d's first. Then I go back to 4p. Then 5s, 4d, 5p, and then 6s. You do not need to worry about the F block. In the DP curriculum, they will not have you cover that. So you just have to worry about 1s all the way through to 6s. But if you did want to get into it, you'd actually first go to the F block, which fits itself in right here. You would start with 4f, then 5d, then 6p, and you would continue reading across. But again, not necessary. A couple things about this notation right here. So we'll take 3p. You'll generally see it as like 3p 3 or 3p4 or 3p5 all the way to 6 because p orbitals can hold 6 electrons. But we have a couple things. The number in front is our main energy level. The letter is our sublevel. And the number is the number of electrons. in the sublevel. So let's go ahead and actually start using this notation. What does it mean to do this? So for this example, I'm going to pick aluminum and I'm going to pull up my periodic table. Cancel. All right, so I have my periodic table here. It's going to be helpful if you always have a periodic table with you, just whenever you're doing chemistry. So let's look at aluminum. So I'm going to find it on my table. I know it's right here. I should switch colors to something that's visible. So if I were to write its electron configuration, the placement of electrons in an aluminum atom, I would start with the top. Now I said helium moved over here. So what you have to do is write every electron in the atom up to aluminum. So we'll start with our first block, which is 1s2. We say 2 because we represent both electrons in the 1s orbital. We then read across and we have nothing else. So we'll drop down. We now have our 2s orbital, and aluminum does have both electrons that exist there. So 2s2. We move over to 2p. 2p. And aluminum does have every electron here all the way to 2p6. Then we drop down and go to 3s. And once again, aluminum has every electron there as well. 3s, not 3, sorry, 2. Remember, the s orbitals can only hold 2. Then we drop down to 3p. Now, aluminum is the first element, meaning it only has one electron, so it would be 3p1. This is the electron configuration for aluminum. Kind of thing. We can do a couple checks. If I look at aluminum, it's element 13, meaning it has 13 protons and 13 electrons. So if I count all the atoms, I should get 13. 2 plus 2 plus 6 plus 2 plus 1. That does equal 13. So we do have the correct number of electrons. We can see that its energy levels, 1 is completely filled, 2 is completely filled, 3 is not completely filled, but that's all right. The s orbital has 2 and the p orbital has 1. So there it is. We can get a little crazy with this by looking at other factors that might affect it. If we look at, for example, aluminum 3 plus, 3 plus indicates that it has lost 3 electrons. We definitely know it hasn't gained protons because if it gained 3 protons, then it would no longer be aluminum. 1, 2, 3, it would be sulfur. But aluminum 3 plus means it lost 3 electrons. So we have to ask, where did they come from? Well, the electron that's easiest to pull out is the one that's furthest away. So it would lose the outermost. I don't know what happened to that S, outermost electrons. So it would lose the P1. So we would have no more P1. I'm just going to copy this over. So we would lose this one. That gives us a 1 plus charge, and then these two giving us a 3 plus charge. And so what we can really see is that aluminum would end up looking like 1s2, 2s2, 2p6. So that is what aluminum 3 plus becomes. The cool thing about that is another element that has that is also neon. We look at neon up here. I'm going to change my colors, maybe something a little brighter. Neon. Neon is also 1s2, 2s2, 2p6. So we can see that it actually has the same electron configuration as neon, which is really, really cool. We can do this with another element. So let's, for example, I'm going to grab this image, hopefully without any of the other stuff. Um, oh, nope, we brought it all with us. We'll just have to delete it. All right. So we can take this same image and help us with iron. Iron, on the other hand, is a little harder than aluminum because we drop into the Ds. We drop into the transition metals. So iron, we're going to do the same thing. We're going to start up here and get 1s2. Drop down, hit 2s2. Move over, hit all of 2p's, so 2p6, 3s2. Hit all of 3p, 3p6. Here, 4s2. And then we move into the 3ds. And we are 1, 2, 3, 4, 5, 6 in. So it's 3d6. So that is our iron. We can similarly take iron 3 plus and lose 3 electrons. Now, this becomes a little more complex. So I'm going to go back to our energy level diagram, keeping in mind that our last orbitals were 4s2 and 3d6. So if I look at 4s and 3d, we want to remove them from the d. But this is where we have this weird notion about the 4s orbital. While we normally remove the outermost electrons, the ones with the highest energy furthest away, we actually remove s before d. So we're going to remove these 2 and the 4s first, and then remove the 1 from the d. So we'll end up with a notation that is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. We'll remove the 2 4s's and 1 from the d6. So keep that in mind when you're doing transition metals. You're going to remove from the 4s before the 3d. And you only need to go to element 36 for the curriculum, so you only need to hit the krypton. So you don't have to worry about anything weird under here. You don't have to worry about any of this stuff. Just up to krypton. All right. So that is our electron configuration. And now to never use that form again, because I'm going to teach you condensed notation. It's far easier. Condensed notation basically says that we can use a noble gas in place of electrons. Now, what I mean is I made the connection earlier that neon is 1s2, 2s2, 2p6. So we could actually rewrite aluminum a different way. So we can rewrite aluminum instead by saying neon with brackets 3s2, 3p1, because neon represents 1s2, 2s2, 2p6. And so because it is the same thing, we can just use brackets to notate it. And so you will never have to do that again. Even if we do iron, we could rewrite iron. And iron doesn't use neon, but we might notice that this entire thing right here is the same as argon. So we can just write argon 4s2, 3d6, and iron 3 plus would just be argon 3d5. And look, all those electrons are gone. So moving forward to the last little bit of this whole lesson. It's a little more than a last little bit, but we're going to go over two exceptions. Exceptions to Aufbau. The two that you must know are chromium and copper. Chromium and copper would both normally be written. They both have argon and normally would say 4s2, 3d4, and copper would be argon 4s2, 3d9. So we'll check our periodic table. Copper is right here. So it would be D1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. and chromium is right here. 1, 2, 3, 4. Cool. Good checks. We like to make sure our work is correct. However, these are not correct. Instead, with these two elements, we write argon 4s1 3d5 and copper, we write argon 4s1 3d10. Now, you don't need to know the reason for it, but it has to do with the fact that a full 3D or a half full 3D orbital is more stable than having the full 4s orbital. However, reasons are not needed for the DP curriculum. You just need to know that this is the correct way to write chromium and copper. All right, moving forward to the last part of this, orbital diagrams. Orbital diagrams. And these are sometimes referred to as arrow in box diagrams, but honestly, I never heard of that until the DP. So, what orbital diagrams do is they actually represent electrons in sublevels, and we use arrows. So, we're going to use up arrow and down arrow to represent spin. So, what does this look like? There's a bunch of different ways to do it. Generally, the two ways are just putting orbitals next to each other in boxes. So right here, I'm going to do an example of nitrogen, which nitrogen has 7 electrons. So this is our 1s orbital, our 2s orbital, and our 3 2p orbital. So I will put 1, and 1s has the lowest, so I'll fill it up. There you go. 2, and then 2p. You'll notice I start with up arrows first. That's the general convention. Now, I don't like this style as much as the other style, which I'll show you right here. It's where you actually put them with their energy. Because when you put them here with their energy, you can much more clearly see why you fill them up in their order. 1s, 2s, 2p. So Aufbau says we fill the lowest first, and then we put our second electron in. Thank you, Pauli exclusion and Hund's rule. 2s, same thing. That's 4 electrons covered. And 2p, we must put 1 in each before we can double up. So we can do one more example. Let's look at oxygen, which is right next to nitrogen with 8 electrons. And we can do it the same two ways. 1s, 2s, 2p. But this time, I'm going to use our diagram with energy taken into account to fill first, 2p. So fill lowest, then next, then 1, 2, 3. So now that I filled each one up, I can finally put my fourth in there. I can transfer this information over to my first diagram and fill that in. And even still, I will always, even if I know what the diagram is, I will always fill in my up arrows before I fill in my down arrows. All right, so hopefully this helps. This is everything that we cover for structure 1.3.5. Have a great day.